Okay, good morning, everyone. Any questions before we start today, or continue, I should say? Last time I had asked you to go ahead and finish up the antiderivative homework and then just look at the first 6. And then, if you wanted to, you could have played with the other problems for the U substitution. So any questions about the method or anything else? We're good. So we're going to just do a bunch of problems today, and then hopefully we'll get into the next section, chapter 6, section 1. So I have a ton of problems that we can work through. We'll just kind of keep going until we feel as a group that I guess we're ready to move on. These first problems here, these first 3 problems, the first one is pretty easy. The second problem and third problem illustrate something very important about the idea of substitution that I think once we do them, you'll kind of get the main idea there. But let's just start with the first one. Remember, we're supposed to look at the integrand. We're supposed to try and identify 2 things, right? Something in there, and then hopefully within the integrand is also the derivative of that something. And it's important that the derivative not be in the denominator, that it not be trapped, and that it could possibly be off by a constant, meaning that when we take the derivative of that something, that derivative can be off by 2 or off by 1/2 or something like that. That's okay. So look at the first one. The first one's pretty straightforward. If you recognize that x squared plus 5x, if that's your u, the derivative of that is 2x plus 5. And that's exactly what we have here, 2x plus 5. So we're going to go ahead and make our substitution that u is equal to the x squared plus 5x. And then the next step is to take the derivative of that with respect to x, which is 2x plus 5. And then I'm always going to multiply both sides by dx here. That's going to happen every single time I ever do one of these problems. I'm always going to multiply by dx. And so moving ahead, all right, moving ahead as we continue to do problems, I'm no longer going to do this step. I'm just going to go to this step. So I'll do du. I'll write the derivative of this here, and then I'll always slap a dx on the end. That's just to cut down on time. Okay, so now what we do is we play this little matching game. Remember that on the original problem, this dx is actually included as part of the 2x plus 5. So 2x plus 5 dx is what makes up this part. So that's going to be replaced with du. And then the yellow part there, x squared plus 5x, will be replaced with u. So we can just rewrite this whole integral as, let's see, the yellow part to the 7th power, so u to the 7th, and then the entire green part becomes the du. And now we just need to know the antiderivative of this. So let's see here. Where were we last time? Let's see, is Aubrey here?
Yes.
Hey, Aubrey.
Hi.
You okay with this?
Mm-hmm.
Okay, so what would be the antiderivative of that, u to the 7th du?
Would be 1/8 times u to the 8th.
Good. And then we'll always do our constant of integration, right?
Yeah.
Plus c. And then the final step would be to do what?
To plug in u.
To replace the u with what we had made the substitution to be. So it's x squared plus 5x.
Yeah.
And then to the 8th plus c. And we're done. Any questions on that? Okay, the second one, I'm going to write the second one down here, and we'll start working with it. So I said the second one and the third one have kind of a unique thing going on that's important. When you look at this, you're trying to identify something in its derivative. There's not a whole lot to work with here, right? All we really have is the 3 minus x to the 10th power. We don't even have two factors next to each other like we did in the previous problem, right? We had two factors, so it was kind of easy for us to see, oh, let this be the something and let that be its derivative. Here, we only really have one thing. It's the 3 minus x to the 10th. So when we're trying to choose our u, we could just try something like, let's just see what would happen if I do u is equal to the 3 minus x. Well, the derivative of that is -1. Everyone agree? The derivative is -1. So the question is, do you see that derivative? Do you see -1? Well, yes and no, I guess. I mean, does everyone agree that there is a 1 out here? Right? I mean, there's a 1 in front of everything, right? So there's a 1 out here. The derivative of this is -1. So wouldn't that be off by a constant then? Like this 1 is off by a constant because the derivative of that's -1. So it's okay. Like we can make this substitution. Let me go to the next line. So I'm going to skip that step where I do du over dx. I'm going to write the derivative of this is -1, and then I'll slap the dx there. So I guess one way you could kind of look at this is if you rewrite this like this and put this 1 dx on the back. So just move that 1 over here. Just you could have imagined there's a 1 right here. This 1 dx is what we have, but over here, it's a -1 dx. So in order for us to get these two things to match, what I'm going to do is just multiply both sides of this equation by -1. So I get negative du equals 1 dx. And when I do that, this now matches this. And we already knew that the 3 minus x was going to get replaced right there. Is that clear, everyone? Okay, let's see. Austin Sansing, are you here?
Yes.
Okay, you doing all right, Austin?
A little drowsy.
Your voice is how I feel right now. I feel like I couldn't wake up today. Okay, so are you clear on what the next line would be? Like how we would rewrite this, what the new integral would turn into?
U to the 10th times negative du.
U to the 10th times negative du. There we go. Good. Now I'm going to do something here. I'm going to take that negative that's right here, and I'm just going to pull it completely out in front as a negative in front of the integral sign. And that's because whenever we have constants, we can always take constants out of an integral because it will just come for the ride, just like in Cal 1 when you had constants in front of functions and you took derivatives, the constant came for the ride. Same thing going backwards. So I'm put that negative out there, u to the 10th du. And then one more hurdle, Austin. What's the antiderivative of this?
Give me a moment. My tired brain's working as hard as it can.
Okay. All right, I can give you time. It's not a big deal. While Austin's thinking about this, just so everyone's clear, you know, our whole idea here is to take an integral, or the original one, whatever, and the entire integral is written in terms of x, right? Everything had x's in there. And then we make a substitution, and our new integral is now in terms of u. You never want to do this and have x's and u's mixed together at the same time. You have to get it all, it either has to be all x's or all u's. So when you get to this step here, that du here and this u to the 10th, That's when we know we've successfully done a substitution, when there's no x's remaining. And then we just go through and do our integration. Hopefully we can integrate what's left. So I think I'm just going to crank this out. This should be, the negative's going to come for the ride, and then the antiderivative of u to the 10th will be 1/11 u to the 11th plus some constant. So just using the power rule there, right? And then last step would be to replace the u with what we said u was, which is 3 minus x, and then that'll be to the 11th power plus c. Okay, we happy about that? Any questions here? Let's look at this last one here before we get some other ones going. 7x plus 9 dx. Okay, this is another problem where you look at it and you're like, well, I don't have a lot to work with here, right? There's not a whole lot to work with. But if you see that the 7x plus 9, if you let that be the u, right, that's your something, the derivative of that is just 7. And again, we always have a 1 sitting here, right? So if we know the derivative is 7 and we have a 1, then we're off by a constant, so we should be able to do this. So the number 2 and number 3 here have the same sort of what's the word I'm looking for? It's the same sort of, not method, but it's the same, they both have the same spirit to them, which is that you can make a substitution of like a linear expression where the derivative of that's going to be a constant, and that will always work because you always have a 1, like no matter what, you always have a 1. So du is just 7 dx. Okay, I have a 1 dx, I don't have a 7 dx, so I'm going to divide both sides by 7, or if you like, I'm going to multiply both sides by 1/7, however you want to look at that. And I don't need the 1 in front of this dx, but I'm going to put it there, and that just helps illustrate again that that 1 dx gets replaced here, and this will be replaced with u. So my new integral, let's see. See, Ian, are you here? I don't see Ian. Adair?
Yes.
Okay, we good?
Yes, I was sort of working it on my own, so I'm
Okay.
catching up where you were.
Okay, can you tell me what the new integral will be?
Yeah, so it'll be root u
Root u,
times 1/7 du.
yep, 1/7 du, good. Now, when we go to do this,
Mhm.
again, the 1/7 I'm gonna bring it out because I can always do that with constants.
Yes.
And then Adair, how would you handle this if you had to take the antiderivative?
Yeah, I would put u to the power of a half.
Yeah, u to the half. And that way you can use your power rule, right? And do your
Yes.
1/n plus 1, u to the n plus 1.
Mhm.
Okay, do you feel comfortable doing that?
Yeah, I do. I just have to write it down so I can
Okay,
see it better. So let's see.
I'm gonna write it while you're working it. And remember, it's at this step, everyone, that the integral sign goes away because we're actually taking the antiderivative. So it's like from here to here, the integral disappears, and you always have to remember to add the c. So this should give us 1/7 times 1/, a half plus 1 is 3/2, and then u to the 3/2 plus c. So let's see, 1/3/2, remember this is really 2/3, right? Just reciprocal. So we're gonna take 1/7 and multiply by 2/3, and we should get 2/21. And then u to the 3/2 plus a constant. And u was 7x plus 9. Any questions there? Okay, so again, the first problem was just as simple as it gets, right? It was exactly here's u, here's its derivative. Everything was perfect. We weren't off by a constant. The second and third problems were examples where you make a substitution and your derivative gives you a constant, just a constant, right? And since we have one next to everything or next to dx all the time, we can always make that substitution. I'll give you another one. Okay. Let's do this one. How about the antiderivative of cosine of 5x dx?
Aaron asked a question in the chat.
Oh, yeah, I didn't. Let me see here. Yes, the question was the du disappears after the antiderivative. So, and this is a very common question. When we go from this line to this line right here, the integral sign goes away because we're actually finding the antiderivative. The du also goes away because the du is kind of like a result of the chain rule. Whenever we do differentiation, you always have, chain rule going on. So you always have something there at the very end, a d something. A lot of times that's turns into a 1. So when you do the antiderivative, it's not there. Well, the way I tell students, if you want, you can actually say that the du doesn't disappear, and you can say it becomes the plus c. If it helps you remember the plus c, then it's not technically what's happening, but it does go away. If you say it becomes the plus c, you'll just hopefully remember to add plus c. Okay, so on this one, we all know that the antiderivative of cosine is sine, but the 5x causes a little bit of an issue. So what I can do is make a substitution, u is 5x, because the derivative of that is just 5 dx. And I have a 1 dx here, right? I have a 1 dx, not a 5 dx. So I can scale this by dividing both sides by 5. And again, now the 1 dx matches the 1 dx. And this part's the u right there. And so when I rewrite the integral, it becomes cosine of u. And then the 1 dx becomes 1/5 du. The 1/5 can come out. And now for this, the antiderivative cosine of u is sine of u. So here's where the integral sign would go away. You have sine of u, and then you have plus c. And then you could replace the u with 5x. There we go. Oh, hey, I wanted to mention, I got an email from the chair of the department today that today we're going to find out whether or not we're going back on campus or not next week. So I'll let you know as soon as I know something. I'll send an email to the class. I'm willing to bet quite a bit that we're not, only because that email that I was sent also included how many new COVID cases we've had on campus, and there's quite a few. So, but I don't know. I don't know what they're going to do. Okay. Yeah. So you know what, this right here actually, what's going on here is when you're taking the antiderivative of cosine of 5x, because of the chain rule, you're always going to have to multiply by 1/5, so 1 over that number, in order to kill off the 5 that comes out if you were to take the derivative of this, right? If I take derivative of sine of 5x, you'll get cosine of 5x, but then you have to take derivative of the 5x, which would give you a 5. And so to offset that 5, I need a 1/5 out here. Now, you can use that idea to get a more general formula for something like this. So think about this. if I were to give you antiderivative of cosine of, let's say, AX. So I just tell you that I have some number in front of X, right? So here A is a constant. Then using this same sort of idea, can somebody tell me then what the antiderivative of this should be?
It'd be 1 over a sine ax, plus c.
Yep, AX plus C, exactly. So do y'all see that? It's this constant right here is always going to be that 1 over the constant here. So this is actually would be a formula that we could remember. And you can go even further. You can modify this a little bit further. You could do not only AX, you could do AX plus B dx. Because think about it. How does this change things? Well, the only issue we have is that when we take the derivative, whatever the antiderivative of this is, when we do the chain rule, when we do the derivative of the inside, we still get A, don't we? It's just A, right? Because B is a constant here. So the derivative of the B would be 0. So in that case, we should still be able to do 1 over A, but now sine of AX plus B. So my point, I'm going to box this one because this is pretty big deal here. So this right here is kind of a general way of how you can find the antiderivative of cosine of any linear expression. Notice that's a linear expression in there, AX plus B. So if you have a linear expression inside the cosine function, all you have to do is scale it by 1 over A and then just do the antiderivative of cosine. Now, how do you think this would work if we changed it and instead of doing cosine, I did antiderivative of sine of AX plus B?
Would we add like a negative?
Yeah, so we know the antiderivative of sine is negative cosine, right? But we still have the issue that we'd have to take the derivative of this inside, which would give us an A. So we have to get rid of that A. So we'd still need the 1 over A. It would be cosine of AX plus B, all that plus C. But again, we need a negative out front because the derivative of cosine is negative sine. So that negative would kill off the negative that comes out from the differentiation and get us back to positive sine. So that is another formula you can kind of, I'm not going to say memorize because it's, I don't want you to be sitting here trying to memorize a bunch of formulas. It's more of a concept. It's just an idea. And it extends beyond sine and cosine. This extends to any function. So let me see if this makes sense with another example. Let's say I did E to the AX plus B dx. So the question is, what's the antiderivative of E to this, right? This is a linear expression. Let's try it. It's itself, right? Plus C. But think about this. If you took the derivative of this, what would the derivative of this be?
E to the ax plus b.
Okay, itself, and then chain rule times what?
Times a.
Times A, right? If I took the derivative of this, the derivative of it would be E to the X plus B itself times the derivative of what's up here, which is just A. So we would again need a 1 over A out front to kill off the A that comes out from the chain rule. Is this making sense, y'all?
Okay,
Right.
so it's the backwards of the chain.
Yeah, we're trying to compensate for when we take the derivative. That chain rule is always going to spit out the A. The A is always going to come out when we do a derivative. And so we have to kind of get rid of it because in the original problem, there is no A out front, right? There's no A out here. So I have to put this 1 over A out here to get rid of it. And this will work for any function, okay? It'll work actually for any function. as long as what's inside of it is linear. That's the key. Okay, so please understand that this only works if this is linear, this is linear, this is linear. Because if it's something different, non-linear, then like, let's just say, for example, this. Let's say we had e to the x squared plus 2x dx. Let's say we had that. You might think, okay, the derivative is, sorry, the antiderivative is this. And then what would go out front? Well, this isn't linear, right? So what's the derivative of this?
2x
2x
plus 2.
plus 2.
X plus 2. So maybe you think to yourself, oh, I'll just put a 1 over 2x plus 2 here, right? Maybe that's what you're thinking. That will not work, okay? The reason it won't work is because if I differentiate this now to check it, we have a product rule here. And that's going to make it extremely complicated. And it's not going to give you this, I promise it won't. But see here, because the 1 over a is a constant, when I differentiate this, there is no product rule. So this is not something that generalizes to anything. It only generalizes to when you have linear expressions plugged into the function. Let's see if you understand this with 3 quick examples. Let me give you a minute to do those, or to see if you can get those. I'll call on some people here in a minute. Okay, let me take volunteers first. I'd like to hear from someone I haven't heard from though. On the first one here, the cosine one. How about Alec? Are you there, Alec?
Yeah, I'm here.
Okay, are you following?
Yeah, I'm still working on it.
Okay. So on these problems, what you want to do is you want to get to the point where you're not actually writing down u equals this and making the substitution and doing all the work. You want to get to a point where you're just writing out the answer. So when I look at this, I say, okay, cosine of this. This is linear, right? That's a linear expression. Now, even though I kind of changed the order and stuff, that was just to confuse you, but that is linear. So as soon as you see a linear expression inside of this, you should just go, oh, okay, well, I know the antiderivative of cosine, right? The antiderivative of cosine is sine. So I'll put sine of that linear expression plus c. But Alec, what do we have to put out front to compensate for the derivative of the inside in the chain rule? So what do we put if we have sine, what was it, cosine of a linear expression? We just put that sine of that linear expression plus c, and then we have to put 1 over a, right?
Yeah, so in that case, it would be 1 over 5, or would it be negative?
1 over negative 5.
Okay.
1 over negative 5. And that's it. See, so we don't want to be doing work for this. We just want to be doing like a visual thing. Make sense, Alec?
Yes.
Okay, Roman, you're up. You get the sine one.
All right, so just sign down at the bottom. And since, or
Antiderivative,
I'm sorry, cosine. And
cosine.
then since the pi x plus pi is linear,
Mhm.
it would stay in the middle. Plus c, and then you would just do 1 over pi.
1 over pi, good. So everyone keep in mind that the number in front of x here, I put pi here to try and trick you again. Pi is just a number, right? So that's the a that's in front of x. Now there's one more thing, Roman, be careful because the antiderivative of sine is negative cosine, right?
Oh, I'm
Right.
sorry.
That's
Yes,
okay.
sir.
No, you understand though? So
Yes.
just throw a negative in front of that.
So
And then 1
negative,
over pi,
got you.
okay? And that'll take care of when you do the chain rule, when you take derivative cosine of something is negative sine of it, that negative you already have out there will kind of go together and it'll make it a positive. Okay, Matthew Gutierrez.
Yes, I'm here.
Okay, are you understanding this?
Yeah, I think so.
Okay, what about the last one?
Okay, so it would be 1 over e,
1 over e, okay,
e, and then to the 5 minus ex
yep.
plus c.
Okay, that's almost right. There's one little thing. You did 1 over e, right?
Yeah,
Okay, and that is right, except what is the a? What's the number in front of x?
e.
Negative e.
Oh, so it would be negative e.
Yep, you have to have the negative there.
Okay.
Yeah, so what we want to do is we want to look at this as being ax plus b, which in our case would be negative ex plus 5. And do you see if I just change the order of things? And this here becomes your a. Okay, this comes up a lot, all right, where we get integrals that involve this, and we don't want to be sitting there doing u substitutions for these. We just want to be able to do them mentally. Again, the key is linear expression. We see a linear expression, then we can do it. Let's do one more, okay, just to show you this extends even beyond these. Look at this one. What if we have the antiderivative of 1 over 1 plus 3x plus 4 squared dx? I know that looks weird, but look at this 3x plus 4. That's linear, right? That's a linear expression. So do you recognize what 1 over 1 plus something squared, what the antiderivative of this should be?
Tangent,
Our-
where's
our
tangent?
Arctangent, right? So let's just think through this. Could it be possible that this is just arctangent of that linear expression plus c, but because of chain rule, again, I'm going to need what out front to kill off that a that pops out?
1/3.
1/3. 1/3. Do you see? So it's in this can be generalized to really anything. But the key is to see that it only works when you have that linear expression in there. Okay, we will have more time for this. So I need to get on to some other problems, some other u substitution problems. So let me go grab a few more. I had some more ready to go here. What I did is I went to a website and grabbed some problems off of here. Let me see. I like that one. We'll do that one. All right. So this is not dealing with that linear thing that I just talked about. This is just, here we go. Let's see what we can do with substitution. And let's see. William Swope is up. You getting this, William?
Yes.
So far, you understand everything? Okay, so we're trying to find something in its derivative. Do you see anything? Let's let William think about it for a moment.
ln of x and then 1 over x.
Okay, ln x and 1 over x. So everyone, natural log of x. Now that natural log of x, it is trapped inside the sine, right? It's inside the sine. Now that's okay. If that's going to be your something, that's okay. The derivative of that can't be trapped, and it can't be in the denominator. So William said, all right, if we let u be equal to natural log of x, William knows that the derivative of that is 1 over x dx. So the question is, do we see 1 over x dx somewhere? Well, yes, but you have to kind of rewrite the problem to see it. So what you can do is you can take that x that's on the denominator and just slide it out to the side as 1 over x. This is the same exact expression as this. And by doing that, now we see the 1 over x dx right here matches. Now you might be saying, well, wait a minute, you said it couldn't be trapped in the denominator, right? Well, nothing is trapped in the denominator. 1 over x dx is exactly the derivative. Okay, that is the derivative right there. So even though it's a fraction, it's not trapped down on the bottom. It's not underneath the square root. It's isolated by itself. So if we let the yellow part be u and the green part be our du, we should be able to rewrite this. So William, what's the new integral that I'd rewrite here?
Sine of u du.
Sine of u du. Okay, and what's the antiderivative of sine of u du?
Negative cosine du
Negative
or
cosine u
u plus c.
plus c. And see, in this case, we don't need that 1 over a thing because this expression inside u is, well, it is linear actually. It's just that there's a 1 in front of it. There's a 1 in front of that u. So then you'd put a 1 over 1 in front. So it doesn't change anything. It's still the same thing. Last step is to replace the u with natural log x. And we're done. I'm going to move this to the side so I can look at it over here. Okay, which of these look interesting? Okay, this one looks like it might be interesting. So the thing is, like, I could come in here and I could do a bunch of problems and I could just show you, oh, here's what u is, here's what u is, here's what u is. The challenge is for you to figure that out, right? So I'm trying to take as much time as I can to allow you to figure it out, but at the same time, like we have to move through material. So, you know, we'll see how it goes here. Ah, come on, there we go. Okay. Aaron, did I call Aaron yet? No, right? Aaron?
No, sir.
All right. How you doing, Aaron?
Great, good morning.
All right. Good morning. All right. So do you see something in its derivative?
Nope.
No?
Mm-mm.
Okay. So you got to try something, right? You got to go with something here. It's like, did I say this last time? Like you have to play the lottery if you're in order to win, right? Like you have to swing a bat in order to hit a ball. Like you're going to have to try something. So
Can I take the, is it called a binomial of the denominator?
you want the denominator? You want to call that u?
Oh, wait. 2x. 3x plus 6.
You want that to be your u?
Yeah.
Okay. If we did that 3x plus 6, what would the derivative of that be?
3x. Or 3.
Dx, right? Which you don't have a 3 dx. You do have a 1 dx, don't you? right? You don't have a 3 dx,
Uh-uh.
but you could multiply both sides by 1/3. And then Aaron, do you agree at this point that I could replace dx right there with 1/3 du?
Yes.
Okay, and do you agree that I could replace the 3x plus 6 with this, with u? Does everyone agree with that?
Yes.
So right now, as we sit, this is what I could do. I could put u on top over x squared plus 4x minus 3, and then I could replace the dx with 1/3 du. And that's where we would be at this point, right?
But isn't
The
it
problem is you still have x's here, right? You need to somehow get rid of these x's. And unfortunately, you do not have a clean way of replacing this. Like you have no way of, like you need to somehow replace x squared and x with something that has u in it. And it's going to get very ugly if we try and do that. So this would be a point, Aaron, where you go, you know what, maybe that u wasn't the right u. Does that make sense, Aaron? That it's still way too complicated, like there's nothing cleaning up and becoming easier?
Okay.
Yeah? Okay, so you tried the 3x plus 6. Try something else.
The bottom portion?
The bottom. All right, let's try the bottom. All right. So in retrospect, Aaron, okay, and going back and thinking about this again, it makes a little more sense to choose the bottom, only because when you take the derivative of the bottom, right, the bottom is a quadratic, right, Aaron? When you take the derivative of a quadratic, you always get what? Everybody?
a linear?
Linear?
Linear function, right? And the numerator is linear, right? So it kind of makes sense that if we start with the quadratic on the bottom as our u, we can cross our fingers and hope that the top is somehow du. We might be off by a constant. So let me try x squared plus 4x minus 3. The derivative of that is 2x plus 4. Is that right? 2x plus 4 dx. Y'all got that?
Yep.
Okay. We have an issue. I mean, Aaron, this is looking pretty good. Like, I know that I can replace this whole denominator with u. Okay, so I'm happy about that. The problem is this. I have 2x plus 4 dx. And up here, I really have, if I wanted to rewrite this, I could rewrite it like this. I really here have 3x plus 6 dx, right? If I just slide this out to the side. These two don't match, do they?
Can you
No.
take the,
We need to get them to match. What's that, Bree?
oh, I was just gonna say, can't you take the two out and then the 3 out and then you have x plus 2?
Oh, okay, so do you all see that? We could rewrite this as 3 times x plus 2, right? Just factor a 3 out of both of those.
Mhm.
And then over here, Bree said you could take out a 2. So that could become 2 times x plus 2 dx.
Yeah, and then move the.
Now we have an x plus 2 in both of these, right? So let's see, what could I do? What could I do equals, let me rewrite this. Here's where we are. We have du equals 2 times x plus 2 dx. And over here, we have that x squared dx. We have that x squared, I'm sorry, x plus 2 dx. We have that in both of them. But we don't have this 2. So Bree, what could I do here?
1/2 du.
Do
So
1/2 on
divide
both
the two.
sides. Divide by 2 on both sides. So see, this is a good example of a problem where we chose a u and the derivative was kind of there, but we were off by a constant quite a bit. We had to do some factoring to actually get it to match. So this right here now matches with this. So let's see if we can rewrite this. I'm going to go back to Aaron because I want to see if Aaron can help me rewrite the integral. So what is this integral going to become? To start replacing things, the green and the yellow, what does this become?
Let's see. 1/2. So it'll be 1/2.
Okay, you want me to put the 1/2 out here?
Right, right.
Okay, good. Yeah, keep going.
And then 1/u.
1/u. Good.
And then x plus 2 du.
The x, look over here, the x plus 2 dx becomes 1/2 du, right?
Oh, du.
Du, okay, du's out here. So here's what we've done, everyone. We've taken care of this, that's that. We've taken care of this, that's that, and that. What's still here, though? There's one thing that didn't go away here.
The 3.
The 3.
Three.
Y'all see that 3? You see the 3? The 3 didn't go away. We factored it out, but it's still there. So we need a 3 here. So let me rewrite it one more time. I'm going to take the 3 out of the integral. It becomes 3/2 integral 1/u du. And that, hopefully, we all recognize the antiderivative of 1/u is
ln, absolute.
ln. Yeah, so natural log absolute value of u plus c. And then the last step would be to replace the natural log, replace the u with what our substitution was, which was x squared plus 4x minus 3 plus c. There you go. Okay. All right, let's do another one. We'll make this one up. All right, this problem's a little weird, a little complicated looking. X e to the x squared over 1 plus e to the x squared, but all of that squared. So let's see here. William, how you doing, William? Little?
Hello.
Okay, so remember, looking for something in its derivative. Do you see anything and its derivative both present?
I can see that the e to the x squared is in the derivative.
Okay, so let's try that. E to the x squared. All right, if we did that, William, what's the derivative of that?
It would be 2? No. 2x. 2x e to the x squared.
Yes. Okay, so what William did here was the derivative of e to anything is itself. All right, that's the e to the x squared. But then you have to do chain rule, do derivative of x squared, which is 2x. So William put it out front. That's fine. It's all multiplication. Doesn't matter what order you're in here. And that's dx. Don't forget the dx here. Does everyone see that? That's the derivative of this. This is the derivative of that. Now, William, do you see this? Because you need to see it somewhere here, and it needs to be maybe off by a constant.
Yes, I see it in the top.
That's
It's
right.
only missing the 2.
Yep, all of that right there is the same as all of this, except for the 2. So William, how would you resolve that issue?
I would multiply each side by 1/2.
Good, 1/2 on the left, 1/2 on the right. And now, yes, this matches exactly. And so when we rewrite the integral, all of the stuff in yellow gets replaced with 1/2 du. And then all the stuff in the green right there, that gets replaced with u. So William, what will the new integral look like? What's our new?
It would, it would be, well, 1/2 would be in the front.
Okay,
Then it would be 1 over 1 plus u squared du.
good. Du, perfect. Y'all see that? William took this integral and rewrote it as 1 over 1 plus e to the x squared times x e to the x squared dx, pulling the yellow part off to the side, the green part being here. Oops, I forgot my square there. So rewrote it this way. Everything in yellow got replaced with the 1/2 du, and then the green got replaced with u. And William, do you recognize this?
Yes, it should be at anti-tangent or arctangent.
Arctangent of, in this case,
U.
u. Okay, so since we had u squared here, the antiderivative, this is 1/2 arctangent of u. And then last step is just to replace u with what u was, so e to the x squared. Let's see. Good. Very good. Well, I'm going to leave that one there. While you're writing that, let me give you another one. This is a tricky one. I like to show this one so that you see something like this for the first time and you're like, oh, okay, well, maybe I wouldn't have thought of that, but now that I've seen this, I might keep my mind open about something like this later. All right, so we're trying to look at this and do substitution. And I hope it's obvious to you that we don't want to let u be x squared, because if we let u be x squared, the derivative of that, even if it was matching, would be in the denominator. We don't want that, right? So maybe we do the denominator as u and hope that maybe the top is du. I don't know. Let me try it. Let me see if that works. If I let u be the whole bottom there, the derivative of this would be 6x to the 5th dx. So do we have 6x to the 5th dx?
No.
No, we don't, right? We have x squared dx. So we're off by more than just a constant, right? I mean, if this was 6x squared dx, we'd be happy because we'd just be off by a constant. But here we're off by like 3 entire factors of x. So you cannot just come in here and try and resolve that. You can't do this. You can't take this side and go 1 over 6x cubed, and then over here divide by 6x cubed and turn that into x squared over here. The reason you can't do that is because now your left side has both x's and u's mixed together. And so your new integral will have x's and u's. So you can't do it. You have to make it, you can only be off by a constant. All right. All right, so this isn't gonna work. So we have to try something else.
Okay, you could do 1 plus x squared or x cubed to the second power
Second power.
squared.
Okay, yeah, so this is the kind of like light bulb moment, is that you have to realize that x to the 6th can be rewritten as x cubed squared.
Oh, and pull out x squared.
How do you mean pull it out?
Like, can you make it 1 over 1 plus?
Oh, sure. If you want me to write it that way.
Yeah.
Yeah, that's fine. I can do that. Like that.
Yes.
Okay. Yeah. Does everyone see what Bree's done here? Rewrote x to the 6th as x cubed squared. And what's great about that is if we let u be x cubed, right? The derivative of that is 3x squared, and we almost have that. We have an x squared. So this is actually going to work. Bree, what made you think to do that?
I think we did a problem last class, something like that, where we
did
just
this in Cal 1. I showed
yeah,
you.
I don't think not this exact, but I
wasn't
remember
exact.
that was a trick. Yeah.
That's a trick. So that's exactly the way that you need to learn it, is that this is something you want to be looking for. And down the road, if you see a problem like this, you want to kind of recognize, oh, hey, I've done this like in the past, which Bree did an excellent job of demonstrating. So this here's our u. The derivative of that is 3x squared dx. We're off by 3, so we will scale it, divide both sides by 3. And now we have perfect matching. That matches that. X cubed is there. And so we can rewrite it as integral 1 over 1 plus u squared. And then 1/3 du. I'll put the 1/3 out here in du. Are there any questions on where any of this is coming from? Like, that is arctangent. So 1/3 arctangent of u plus c, but I'll go ahead and replace the u right now. I'm just going to go ahead and replace the u with x cubed. This should be our antiderivative. Okay, let's do one more. Let's do one more. And this is another kind of classic problem that you should see. Y'all ready? We can go to the next page. All right, so here it is. And for those of you who had me for Cal 1, this is the end of the road as far as stuff that you've seen. Like from here on, it's going to be brand new stuff. All right. Okay, here we go. So if I wanted to do x and then x plus 4 to the 80th power dx. All right, so when you look at this, you can start thinking about like, what do I let u be, right? What's the substitution? Well, you could let u be x, right? You could just let u be x. But whenever it comes to u substitution, I'm going to say this one time, don't ever let u just be x. Because if you do that, what will happen is you will rewrite the whole problem in terms of u. In other words, everything in the problem will just, it's like all the x's will be replaced with u's and you won't do anything to advance in the problem. So never let u be x. It's got to be something other than x. So what's the only other choice we have here? What appears to be the only other real choice? X plus 4. And what would the derivative of x plus 4 be?
1.
1.
1, which we have a 1, right? But it doesn't really seem like that's going to get us anywhere. All right, so let's just do it though anyway, because we got to try something, right? We got to go buy the lottery ticket. So here it is. right? U is x plus 4, du equals 1 dx, which I have right there. I have a 1 dx right there. So 1 dx will be replaced with du, and x plus 4 will be replaced with u. Right? So everything's good so far, with the exception of this x. The question becomes, what does that x become? Right? We know what x plus 4 is, right? That's going to be u. We know that the 1 dx is going to become du, but what does x become? Any ideas? You have to change it to u's, because remember I said you can't have x's and u's mixed together.
U minus 4.
U minus 4. So where are you getting that from, Ian?
You just you isolate the x and u equals x plus 4.
There you go. So Ian's saying, well, wait a minute. We made a substitution. We said that u is equal to x plus 4. So if I want to know what x is, all I have to do is just move the 4 over, and I can tell you that x would be u minus 4. So now we have something we can replace the x with, right? The x can be replaced with u minus 4. And then we can rewrite the whole integral. So the x becomes the u minus 4. This next piece becomes u to the 80th power. And then the dx becomes du. Any questions on that? Did that actually get us anywhere? Did we actually make any progress on this? Because, I mean, the original problem, we went to the substitution, but this doesn't look like we gained much. Did we or not? Did we gain anything here? Did it get better?
Well, no, because there's a product, right?
This is a product, right? Yeah. But can't you just distribute this like algebra? Can't you just distribute that through the parenthesis? Could, right? What would happen if I did that? U to the 80th times u would be u to the 81st power, right? And then the next term would be minus 4 u to the 80th power du. That's just algebra, isn't it? And now, because we have subtraction between these two, we can do them individually. And each one of these individually, we can use power rule on, can't we? The power rule. So Jimmy, what would the antiderivative of, where's Jimmy? Is Jimmy here? I see Jimmy. Jimmy, you there?
Yes, sir. Sorry, I was trying to mute myself.
Okay. So do you understand we're going to be able to do the antiderivative of each of these separately because we have subtraction?
Yes.
Okay, so using the power rule, can you give me the antiderivative of this? Of u to the 81st power. I'm sorry, did you say something?
Oh no, it's because I was just trying to figure it out because I'm trying to refresh myself on the power rule because it's been a second.
Okay. So the power rule, all you're going to do is add 1 to the power, right? Just add 1 to the power. So it's u to the what?
Oh, to the 82nd.
82nd. But because you're going to have to kill that 82nd off with the chain rule, you have to put out front 1 over.
Oh, 1 over 82, right?
82 also. Okay, good.
Okay,
And then we'll have
okay,
minus
the other one will be, yes.
Mm-hmm.
And then it'll be 1 over 82 u over u.
81 u to the,
181. Oh, my fault.
Yeah. Then plus c. Which is 1 over 82. U is x plus 4 to the 82 minus 4 over 81 u, which was x plus 4 to the 81st power plus c. There it is. That's the antiderivative. Now, why couldn't, in the very beginning of the problem, why not just save ourselves all this time and just distribute the x through here instead? Like do this first and not have to do all this. Can I do that here? Could I have algebraically distributed the x through?
You need to respect the power.
Respect it. Yes, thank you. That's one way to put it, right? Order of operations. You must do the exponent here. You must expand this out first before you distribute the x. You're not allowed to push this x through until you've done the 80th power. And I don't think anybody in this class wants to do x plus 4 times x plus 4 times x plus 4 times x plus 4 80 times, right? And then pass an x through at the end. So that algebraically would be something that would be not really feasible by hand, right? But using this really cool substitution that didn't really seem like it was going to get us anywhere, we're able to rewrite the problem, and then we could do a distribution because the order of operations here, there's no power on that u minus 4, there's a power of 1, right? So we don't have to worry about doing any expanding, then we can just distribute the u to the 80th through. So it's kind of amazing that that substitution allows us to do the problem, but it does. So I guess the moral of the story again is you've got to be willing to try a u substitution, right? It's not always going to be obvious. It's not always going to be like that first problem we did, where it's like, oh yeah, there's u, there's its derivative, boom, we're done, easy money, we move on. Sometimes it's not so natural, or especially like the one before, right? Not a very natural substitution. Okay, any questions? All right. No? You need to make sure that you do this homework set, all right? Substitution 1 through 36, do all of them, okay? You're gonna learn a lot doing that homework. And just remember that I have my solution videos there for you to use as a guide, you know, but remember, don't just watch my videos. I mean, you try the problem, use my video as a guide to kind of see if we're on the same track, all right? Okay, we're ready to start the next topic. So the way I'm going to do this before I start is I'm going to give you a problem to look at. I'm going to give you an integral, and I'm going to have you see if you can't figure out what it is, the antiderivative. And I'm not going to let you spend forever on it, okay? I just want to give you like 5 minutes because I want you to just think about whether or not we have the tools in place to be able to do this. Okay, here it is. There we go. Pretty simple function, pretty simple integral, x cosine x. Seems like we may have enough to do that, but I want you to mess with it for about 5 minutes. If you think that you've got a way of doing it, like if you think you've figured it out, check your answer by taking the derivative. And it better come out to be x cosine x. Do you give up yet?
Almost.
Okay, so look, if you don't know, if you haven't learned this next technique, then there's nothing you're going to be able to do. You spend the rest of your life trying to do this problem, you'll never figure it out. Okay, because there's nothing that you've been taught to teach you how to do this yet. So I drew a picture here. I know it's a great picture, right? I've got a screw that I'm trying to put into a board, and I've got a hammer, right? So I have the wrong tool for the job here. And so right now you don't have the right tool for this, right? So I have to give you the tool to do this problem. Now the tool is a formula. Now we don't get a lot of formulas in Cal 2 when it comes to finding antiderivatives. And so you might be happy to hear about this formula, but just let me explain the formula first, and then you'll understand even though it's great, it also adds multiple layers of complexity to things, all right? So right now, we have a hammer, we need a screwdriver. Probably a powered screwdriver, that'd be even better, right? Okay, so here we go. I need to introduce you to your next tool. I'm not even gonna talk about what it is yet or what we call it, all right? I wanna show you where it comes from, all right? So let's go back to Cal 1, all right? And let's say we're given a function f of x and some other function g of x, all right? We're given those. Now you're taught in Cal 1 that if you were to take those two functions and multiply them, and then be asked to find the derivative, you would have to use the product rule, right? So the product rule says that the derivative of f times g should be the derivative of f times the g function plus the derivative of the g function times the f function. Now I know that you may have learned this formula a little different, you know, things might be flipped over, rearranged, but we all should have the derivative of the f times the g somewhere in our formula, and then somewhere else the derivative of g times the f, and then add them together, right? So everyone's happy with the product rule. We're not going to question where that comes from, right? We all agree with that. We're okay with it. Okay, now remember, the antiderivative is the inverse operation of the derivative. Okay, so it's like if you take a derivative and then the antiderivative, you go back to where you started. Does that make sense? So what I'm going to do right now is on both sides of this equation, I'm going to do the antiderivative. Okay, so I'm going to do the antiderivative on the left side and the antiderivative on the right side, and it's going to be dx. In other words, treating x like the variable, because these are both functions of x. So on the left side, I had two functions being multiplied and I had their derivative, but then I'm taking the antiderivative, so that should undo this derivative. So what should be left on the left side?
F of x and g of x.
Yeah, just those two multiplied together, right? Okay, so it's like I took their product, I took their derivative, but then I undid that derivative with the antiderivative, so it just should be the product of those. Now, on the right-hand side, we have a little bit of an issue because we have addition, right? We have addition and we have two terms. So that antiderivative will be applied to the first product. And then the antiderivative would be applied to the second product. And that's just because what we've already learned, the way the antiderivative works is that if we have a sum or a difference, we can do them individually. So do you all agree with that step? I still have no idea. Okay, look, I have no idea what this is. I have no idea what this is. I do know what this is because the derivative was out here on this entire thing, right? So taking the antiderivative of that entire thing kills everything off and just gives you back this. Here I cannot do the same thing because the derivative is only on the f. And so I cannot say that this undoes just the f. It's more complicated than that. Same with this. The derivative is not on the whole thing. Do y'all see that?
Yes.
Well, believe it or not, this is the tool. This is the actual tool. It's just not written quite the way we're going to use it. So watch what I do here. Let me think about this because I want to make sure so what I'm going to do is this. I'm going to rearrange this equation. I'm going to take everything here, that entire integral, I'm going to subtract it from both sides of the equation. And so I subtracted on this side also. So I get a new equation. Here's the equation. It is, the left side is the f of x times g of x. That was this piece here. And then I subtracted that integral, so that minus, and then it's going to be g prime of x times f of x, right? This one. I'm going to rearrange it though. I'm going to say f of x times g prime of x. That's because multiplication is commutative. It doesn't matter how you write that. And then equals the right side. The only thing that was left on the right side was this one, right? The yellow one. And I'm gonna also rearrange that one to be g of x integral g of x f prime of x dx. Go with me? All right. This is the actual formula. Now, it may look crazy to you right now, so I'm gonna do something to make it easier to work with. All right, because this right here just looks nuts. What I'm gonna do is I'm gonna go back up to this up here where I said f and g, and to make our notation easier, what I'm gonna do is I'm just gonna call the g function u. All right, and I'm gonna call this f function, let's call it v, just for the simplicity's sake. Then let's try and rewrite this formula. What is the f function? Well, I'm kind of running out of room here, so let me try this. The f function is v, right? The g function is u. Do you agree? Minus the integral. What's the f function?
V.
V. And then times the derivative of g, right? Well, if g is u, then this will be the derivative of u, right? Like that. And then equals the integral g was u, times the derivative of f, but if f is v, this will be v prime. You okay with that? All right. I've got more work to do. You know what? I may be able to do it here. Okay, I'm going to do some rearranging again. All right, I'm trying to get to a final formula. What I'm going to do, since this is an equation, it doesn't matter which way I write it. So I'm going to write this right side. I'm going to actually write that on the left side. I'm going to write u, and instead of v prime, I'm going to write dv to represent the derivative of v, dv. This is the v prime. Equals, now the left side, you see how we have v times u? I'm going to write it backwards, u times v. And then minus the integral, and then this one I'm going to write v, and instead of u prime, I'm going to write du. So dv stands for the derivative of the v function, du stands for the derivative of the u function, and then u and v are just those two functions respectively. This is what we refer to as the integration by parts formula, IBP, integration by parts, all right, IBP. Now there's a cute little clever way to remember this formula. The little clever way to remember, and this was told to me many years ago when I first learned it, is this little saying: ultraviolet minus voodoo. Is it VOODOO? Voodoo? Is that how you spell voodoo? VOODOO?
Two O's, yeah.
Yeah, two O's, right? Voodoo. Ultraviolet minus voodoo. Okay, so look at this formula. Let's read the right-hand side. Ultraviolet minus voodoo. Ultraviolet minus voodoo. Now you need to remember that there's an integral sign here. You have to remember that. That's not in this. But so if you wanted to, you could add this in here. Minus integral voodoo. All right, there it is. All right, there it is. Now it's actually in your formula sheets. Right here on page 6 are the table of integrals, common integrals, and the very first formula is the integration by parts formula. The integral of u dv is equal to ultraviolet minus the integral of v du. Ultraviolet minus voodoo. Right? It's right there. So you don't even need to remember it, like you have a reference to it, but it's there. All right. So what the hell is this formula doing? Right? What in the world? Why? How is this even useful? So let me write it down again. So if we have an integral and we have u times dv, this will always be equal to u times v minus the integral of v times du. So the spirit of this formula is this. You're going to start with an integral, okay, that's presented to you, okay? You look at it and you go, shit, I have no idea how to do that, right? This formula allows you to create, well, first of all, there will be some junk here that's going to be out front. But the important thing is that it allows you to create a new integral. A new integral. Gosh, I can't write. And there's something very, very different in this new integral than the original one. The original one had u, which is some function, and then it had the derivative of some other function there. Right? So imagine there's two functions, u and v. One of them is right there. There's u, and there's the derivative of some other function v. In the new integral, they trade places. Instead of having u in the new integral, it's the derivative of that u. And instead of having the derivative of v in the integral, we now have v, which is the antiderivative of this. So I remember my professor, Dr. Richardson, telling us this, and he was trying to drill this into our heads. The integration by parts formula does something very special called the transferring of the derivative. We are transferring the derivative. It goes from one function to the other, and then the other one, the antiderivative, gets transferred. The only way to truly see this in action is to do an example. So let's go to the problem that I gave you a minute ago. That problem right there. Right, we had already said we can't figure that out, right? We can't figure that out. But I have two functions here, right? I have two things being multiplied together. So this is my starting point. What I need to do is I need to figure out what's my u and what's my dv. So one of these guys, either the x or the cosine x, one of them is going to have to be the u, and the other one is going to have to be the derivative of some other function v. In the new integral, I will be working with the derivative of u in the antiderivative of that thing that was over here. So you look at this and you have to make a decision at this point. if you're going to use this formula, you have to make a decision. Which of those are you going to call u, and which of those are going to be the dv? So does anybody have a, not a guess, but like an idea of which of these should be our u and which should be the dv?
Is ux?
Okay, let's try that. What if u is x? So let's think through this. If this is u, right, if we're going to call that u, that means everything else that's left must be the dv. Understand? Now, Roman's saying, let's do this. Let's see if Roman is right. Before you write anything else down, I want you to mentally think about this. The new integral. So imagine we're thinking, right? We're thinking about this new integral. It's in our heads. We see the integral, right? Roman, you see it? In that new integral, we're not going to have u. What are we going to have?
Du.
The derivative of it, right? So if Roman, if you said that this x was your u, what is going to be in the new integral? Not x, but what? What's the derivative of x?
1.
1, right? 1, or you could say dx, 1 dx. So you're thinking, oh, in this new integral, I'm going to have du, that's 1 dx, okay, right? And then also in the new integral, you're going to have v, which should be the antiderivative of this. So Roman, what's the antiderivative of this?
Sine.
Sine. So that would be here, right? Sine x. Now you're visualizing this. You're saying, okay, I started with u being x, dv is cosine x. In the new integral, I'm going to have the derivative of x, which is 1. And then I'm going to have the antiderivative of cosine, which is sine. So I got sine times 1. I'm happy about that integral, right? Like we can do this integral. That's not a hard integral. That's just the antiderivative of sine. Do you see that? Does everyone see that? So so at that point, you're like, yes, that should be what I do. Now, I want to run through this again, but I want to say, what if we switched it? What if instead of doing this, Roman would have said, let's let the cosine x be the u, and let's let the x dx together be our dv, okay? Do y'all see the difference by approaching it this way? So I'm going to stick with you, Roman. Roman, in the new integral, right? In the new integral, we're going to have the derivative of u, and we're going to have the antiderivative of this thing, right? So what would the derivative of u be in this new integral? If u is cosine x.
Would it just be x sine?
What's u here? What have I chosen to be u?
Oh, cosine x?
Cosine x. So what is the derivative of that going to be in the new integral?
Sine x.
Negative sine x, right?
Negative sine x.
Okay. That's not so much of a problem, right? Sine x dx. I have to put dx because I'm taking the derivative. But here's the issue. Roman, that means that the x dx was the dv, right? So Roman, what's the antiderivative of x?
X squared.
Yeah, power rule, right? 1/2 x squared. Right? 1/2 x squared. Do you see that? Everyone
Yes,
see
sir.
that? And then look, going back the other way Roman did it, it was this. You have these two integrals that it could possibly have become, right? Which of those is doable?
The first one?
First one, right? The second one is actually more complicated than the first one, because now you have an x squared here next to the sine, which is even worse than what you started with. So again, the idea of integration by parts is that you're going to start with an integral that you don't know how to do. You're going to pick a u and a dv, and you're going to try and think about what it becomes in the new integral. And if it looks like it's going to get better, then that's the way you're going to go. All right, we're going to start that problem from scratch, and I'm going to show you how I do problems like this. Okay, here we go. I look at it and I say, okay, I don't know how to do it other than bringing out the integration by parts. So I'm seeing right now that if I let that be u, the derivative of that in the new integral is 1, and I'm happy about that. That means the rest of this would be the dv. The antiderivative of that in the new integral will be the sine of x. So how do I actually start executing this formula? what I do, and this is different for everyone, just this is the way that I've always shown students, is I make a table. I put in the top left corner, I put what my U is going to be. In the bottom right hand corner, I put what DV is going to be. So I get to make those choices, right? I get to make that choice. Now, let me fill out the rest of the table. Anytime we move down on the table, it's a derivative. So if I move down, this is du. And for dv, I move up in the table, so that takes me up to v. So I'm going to fill this table out. U is my choice. I made the choice when Roman made the choice initially of x, right? As being the u. And then that made this whole thing in green have to be the dv, cosine x dx. Make sure you include the dx with the dv. Now all I do is I go down the table, so I differentiate this. This will be 1 dx. Make sure you put the dx because the derivative of x is 1. But again, just like we did when we were doing substitution, that dx will appear. And then here we got to go up. So to go up, this step right here, from here to here, is an antiderivative. That's an antiderivative right there. So you need to know what the antiderivative of that is, and it's sine x. Y'all see how I filled out the table? Once I filled it out, I go to my formula, ultraviolet minus the integral of voodoo. I'm going to fill this out. So the left side is our is our UDV. That's the left side. This should be equal to U times V first. So it's going to be this times this, straight across. So that's x sine x minus the integral of V. V was sine x, times du, but du is 1 dx, so I'm just going to put dx. And now, I mean, that's just a pretty basic integral. I mean, it's x sine x minus, okay, the antiderivative of sine x is what? The antiderivative of sine x is
Negative cosine x.
negative cosine x. So negative cosine x. And then don't forget, I'm going to have a plus c because this is an antiderivative. Maybe one more step, x sine x plus cosine x plus c. There it is. Now I'm going to check my answer. I want to show everyone right now that this is correct. And to do it, I'm going to take its derivative. So I'm going to take derivative of this right now. Ready? If I take the derivative of that, I have a product right there between the x and the sine. So I have to apply the product rule here. So I'll have the derivative of x, which is 1 times sine x, plus the derivative of sine x, which is cosine x, times the first function, which is x. So that's my product rule here. And then I have plus the derivative of cosine. So plus the derivative of cosine, but the derivative of cosine is negative sine. And if you look at this sine x cancels with that sine x. And all you're left with is this, which is really x cosine x. And that was the original integrand. And so it is, in fact, the antiderivative. Pretty awesome. Very, very powerful, the integration by parts formula. But it all comes down to you picking the right thing for the U and the DV. I have 4 minutes. Let me see if I can get one more in here. What about this one? Okay, so let's first fast forward because we can't do this with any other method. So basic U substitution is not going to work. So fast forward, you've tried some other things, you're stuck. Here you go. You've got to pick a U. We're doing integration by parts. We've got to pick a U. And we've got to pick a DV. Anybody have any ideas of what we should pick for U and DV? You have two things there, right? You have an X and you have a natural log X. One of those has to be U.
U
Make
should be
U
X.
L.
You want to try U as X?
Yeah.
Let's try it. If U is X, then what does DV have to be?
Natural log of X.
Everything else that's left, right? Natural log X dx. Okay, so that's our first option. Okay, that's one way we could do it. Let's see, will this work? So complete the table, differentiate down. What's a derivative of X?
1 dx.
1 dx, okay. And then now do this one, integrate up to V. And that means you need the antiderivative of the natural log of X. Uh-oh. You don't know the antiderivative of natural log of X. You know the derivative of it, don't you? But you don't know the antiderivative. So that ain't gonna work. That ain't gonna work. So even though it seemed like picking X to be U would be good because in the new integral, right, it's gonna become a 1. This actually doesn't work because we can't integrate up, which means you really have to go with the other option. What's the other option? U is this, what's DV? So tell me what U is here. If we can't use this one, then that forces you to put what here?
Natural log.
Natural log of X. And then that forces you to put the other piece here, X dx here. All right, let's complete the table. This will be the derivative of this, which we know is 1 over X dx. Okay, derivative of natural log of X is 1 over X dx. And then we have to integrate up to get V. What's the antiderivative of X? 1/2.
1/2 X
squared, right?
squared.
1/2 X squared. So when I'm doing these problems, what I usually do is I think to myself, I'm always thinking about that last integral in the formula. The new integral will always be voodoo. Okay. Voodoo is the integral that comes at the very end of the formula. Where is it? Right there. Integral voodoo. I'm always thinking about that integral voodoo. Voodoo on your table, voodoo is always this and this together, multiplied. That's V and that's du. So think about this. If you were to put these two together with multiplication, could you handle it? I think so. Let's see. This will become, according to the formula, ultraviolet, which will be the natural log X times 1/2 X squared minus the integral of voodoo, V, times du, which is that. So there's voodoo. And do you see how this just cleans up, right? X squared over X. I have here natural log X times 1/2 X squared minus 1/2 integral of X dx. So what I did here, I know I'm out of time. What I did here was I pulled the 1/2 out, and then X squared over X is just X. And I hope everyone's comfortable with the antiderivative of X, right? 1/2 X squared. So here we go. I'm going to do my antiderivative, natural log X times 1/2 X squared minus 1/2. Now times, now the antiderivative of this, which is 1/2 X squared plus C. If you need to go, you can go, but I'm going to finish this. All right, so I'm going to write my final version here. I'm going to kind of rewrite some things. I'm going to put 1/2 X squared, then the natural log of X. And then minus 1/4 X squared plus C. So I just kind of switched the order of these just because that's the way I like to write it, and then put these together. That should be the antiderivative. That should be it. I'm going to check it real quick. Take derivative. There's a product rule. Derivative of the first one is just going to be x times the second one plus derivative of natural log, which is 1 over x times the first one, 1/2 x squared, and then minus the derivative of this one, which is 1/2 x squared, or sorry, 1/2 x. Okay, so I went real fast through that. This and that cancel out 1x, and then you can see that these two are the same but opposite, so they kill each other off, and then all you're left with is x outline x. It works. Okay, so what are we doing? For homework, make sure you do the 5.5 substitution homework 1 through 36. Do that. And then the integration by parts, don't worry about starting that yet. We'll come back and we will get deeper into it. We have a lot of problems to do in this section. But you've got to have the substitution down first, or else the integration by parts becomes really difficult. We're supposed to have our first test on the 13th, right? And that means we don't have class on Monday. By the way, we do not have class Monday, whether it be on campus or on Zoom. We do not have class Labor Day holiday. So I will not see you again until Wednesday. And then after that, we have a test. So notice that on the schedule, I have integration by parts here, right? I have integration by parts, but I also have it after the test. So the first test will include some integration by parts, but it will be easier problems, easy ones. And then after that, we'll do harder ones, and that'll be on exam 2. Okay, any questions?
I have a quick one on it. Say that we are online for exam day. What are the like you said, there were specific rules if we were going to take it online, and you had to go over them if we were going to be online?
Yeah, I mean, it's just going to be a matter that you have to set up your camera so that I can kind of see what's around you.
Oh, okay.
Yeah,
sure.
that sort of thing.
And then like it's during like class though.
Yes.
Like we attend the exam. Got you. All right.
Yep, you attend the Zoom. Yeah, let me see. I'll check my email. I'll send y'all something. I don't know if they've updated anything on the website yet. Who knows? Let me see. Maybe they did. Northwest roll. Let me see if there's anything in my email. Okay. Let me see. Yeah, this is no, that's not. Yeah, this is the most recent thing I have. The plan for week 3 will be mostly announced on Wednesday. So that's the most recent thing I have. So I'll let you know. I'll let you know as soon as I find something out. I'll let you know what's going on. I'll send an email in Canvas.
All right, thank you. Have a good weekend.
Yep.
When do you think you could get a review to us?
Review for
The exam?
what?
Are we
review?
gonna get one? Like a review for the
Who said
exam?
review? Who said there
Are we
was
not
an
getting
review?
one?
That's a great idea. I agree.
Who said there would be a review?
Hopefully you do in about
On the
2
syllabus.
seconds.
Yeah. Remember what I said in Cal 1 though about reviews? No?
No.
I said I was giving you all reviews, but not like it's not something you should get used to, you know. I'll give you all something. I'll give you all something, but I'm trying to wean you all away from it only because it's for your own good. I'm trying to wean you away from needing that thing, that safety blanket, that little whoopee, you know. You want to get to a point where you feel confident in the material that no matter what I present you with, you feel good like you can do it. And that just means that you know how to do the homework, but I'll give you something.
Okay.
So when, I would say probably next week.
Okay.
Yeah. And What I may not do is give you the solutions. I may, you know, if you want to come and ask me, did I do this right or something like that? Yes, but you know. Okay, that sound fair?
Sounds fair.
Okay.
All right, thanks.
All right. Have a good weekend.
And the exam one, what is that one gonna